Here's a nice kinematics question which explores the idea of relative velocity as seen from the perspective of an observer that is rotating. Okay, and we're gonna explore this misconception in a couple of steps. Now, if you'd like to see anything similar to this, or if you have any suggestions on topics or specific problems that you'd like to see on the channel, please let me know in the comments. So, this question involves two cars called car B and car A, and they're traveling in slightly different ways. So car A is traveling in a straight line with constant speed v, which means that car A has a constant velocity, and car B has a constant speed, but is traveling along the arc of a circle with a velocity that's always changing. And the question is asking us to prove that the velocity which A appears to have, so that's the key here, it appears to have, to an observer riding with car B, is zero when car A passes the position shown, regardless of the angle theta. Okay, so let's try to talk about this relative velocity idea first. So if there are two cars on the road, let's say car A is stationary and car B is moving towards car A with a speed of maybe 10 meters per second. So it's that way with 10 meters per second. So if I'm the one in car A, I will see the velocity of car B as being minus 10 I meters per second. So I'm using vector notation here just so we can take the signs into account. So the minus here tells us that car B has a negative direction with respect to what I consider my positive x direction. So my positive x direction is to the right. Okay. Now, if I'm in car B on the other hand, and if I look at car A, I'm going to see that the velocity of car A is going to be plus 10 meters per second. So the reason for that is because when I'm in car B, with respect to me, my car is stationary, but I will see car A coming towards me instead with this speed, which is in the positive x direction. So the question is, does this apply to a rotating coordinate system as well? So what you can see here is that when you change the perspective from A to B or from B to A, the magnitude, the 10, stays the same, but the sign changes from minus to plus. And this corresponds to what our intuition might tell us. But when we deal with rotating axes of coordinates, with rotating coordinate systems, uh, things are not as straightforward as you'll see in a second. So, first of all, what the question is basically asking us to find is the velocity of car A relative to car B. Okay, and I'm going to call this VRL, or V relative. And before we even find this, what I would like to do first is shift my perspective. So I will try to find VB with respect to A. In other words, I'm the driver of car A and I'm looking at car B and I'm trying to find what the relative velocity of B is with respect to me. So to do that, let's see what the steps are. First of all, I'll say that the velocity of A will be equal to v times j meters per second. Okay, the reason I said that is because my coordinate system looks something like this. So x is to the right, my positive y direction is upwards, and car A is traveling straight along my y-axis, meaning that it only has a y component which corresponds to the j unit vector. And then we have to do the same thing for B. But as you see, car B is not actually traveling along one of my directions only. Instead, what we have to do here, we have to decompose this velocity in two. So let's see how we can actually do that. So that's the velocity that we're trying to decompose, and this is my y and this is my x. Maybe I should have used red. Like this and like this. Okay, so now we should use a bit of geometry to figure out uh, what's the deal with this angle theta, basically. So the obvious thing to note at this point would be that this angle here is theta, okay? Because um, my vertical y-axis is perpendicular to this, and then the blue arrow for v is perpendicular to this, which means this angle here is the same as this angle here. Okay, now what that means is the following. So the velocity of b has an x component, which is v sine theta I plus v cos theta j. Okay, and that's because the velocity is like this, and my coordinate axes are like this. So we have y here going up, and we have x going this way, and then this angle here is theta. So this component is v sine theta, and this component is v cos theta. So it's just trigonometry at this point. There's nothing special going on, right? And this is v. Okay, so let's try to find what vb with respect to a is. So if I'm in car A, what do I see? What's the velocity of car B that I perceive? So here's how we can do this. The velocity of B equals the velocity of A plus the relative velocity of B with respect to A. I could write this. And then plus omega cross, and that's going to be the position vector of B with respect to A, which is AB. So I'm just applying Euler's equation for velocity. Now, one thing we can note straight away is that this term, in this case, is 0, because what I'm actually doing is I'm traveling with car A. And if I'm traveling with car A, my coordinate system is attached to car A, and car A is not rotating. Car A is just traveling straight, which means my coordinate system is not rotating either, which means that there's no angular velocity of the coordinate system, which means this term is just 0, which means that the velocity of B with respect to A equals VB minus VA, which is what we sort of expected from the beginning. So that is V sine theta I, and then we have plus V cos theta j, and then minus, and VA is just VJ, okay? And what we can do is we can separate the i's and the j's. So we have that the velocity of B with respect to A is equal to V sine theta I plus J. And then we can factorize V as well, and that's going to be cosine of theta minus 1. Okay. So with respect to car A, car B will have this velocity. And as you can see, this velocity 100% depends on the location of car B on that circle, because there is sine theta, there's cosine theta. So as long as there is something that has to do with the angle theta, the relative velocity depends on the position of B. But that's not what the question is asking us to do. The question is asking us to find this relative velocity. So in other words, I'm the driver of car B, and if I look back at car A, what is the relative velocity of car A in that case? So to do that, once again, we're going to use Euler's equations. So this is what we have. The velocity of A is equal to the velocity of B. So now my coordinate system is here. So I'm going to erase this one. I'm going to erase this whole bit, and I'm going to erase this one too. So this is my new coordinate system attached to car B, and it's rotating with car B as well. And if we apply Euler's equation for velocity, this is what we have. We have VA is equal to VB plus the relative velocity, that's what we're trying to find, plus omega, and then we have cross product with BA, like that. Now this is no longer zero because this is now the angular velocity of the car B, which is the same as the angular velocity of the coordinate system, which we can actually find quite easily. So the magnitude of that is actually equal to V over R. That's the definition of angular velocity. There's nothing special here. The only thing to note is that when we convert this into a vector, this should be minus V over R multiplied by K. And the minus tells us that car B, as you can see here, is doing a clockwise rotation about the center of the circle. So a clockwise rotation means we use a negative sign, which is what we're doing. So let's write what the relative velocity is. So the relative velocity is VA, and then minus VB, and then minus omega cross BA. Okay, so let me make this a bit more clear like this. Perfect. So VA is V times J. Okay, we established this earlier. And then we have minus. Now we know what VB is, but I'm not going to write VB as what we found earlier. Instead, I'm going to do something that will make our life a bit easier. Namely, I'm going to write that the velocity of B is omega cross OB, right? And that's what the velocity of B is also equal to. It's the it's the angular velocity of B cross product with the position vector of B with respect to this point O right here. So we're just gonna leave it like this and you'll see why. And then minus omega cross BA for our third term. So that's the relative velocity, which I'm gonna move to the next page. So the relative velocity is Vj minus, and what we can do now is we can factorize omega, right? We have omega and then cross, and then we can add up OB and BA together as vectors. So that's vector OB plus vector BA. And according to the vector addition rules, this is what's going on. We have vector OB as this vector. So it starts at O and the arrow is pointing towards B. And then BA is this vector here. So starts at B and ends at O. So if we add them up, what we actually get is this here, which is the distance from O to A, which is purely in the x direction in this particular moment. So I'm going to replace this here with OA. And just as a note, OA, we actually know what OA is. So the length of OA is the radius of the circle, which is minus r times I. Of course, there's a minus because OA is in the negative x direction. So that's what we have. Now the relative velocity is Vj minus, and let's write our determinant. So we have ijk, and then my omega is 0, 0, and minus v over r. And this is minus r, 0, and 0. Okay, so the relative velocity equals Vj minus, and the determinant only has a j component basically. So that's going to be minus j multiplied with v over r times r. So the two minus signs cancel out. So we get this, and of course the r's cancel out as well, and we get vj minus vj, which is 0. Should write 0j, doesn't really matter, but or let's just keep it as 0 meters per second, like that. Which is very interesting because that's not what we would have expected if we found our relative velocity the other way around. So when we're in car A, and if we look at car B that's going around the circle, we will observe car B having this relative velocity, which of course depends on the angle theta. But if the opposite is true, if we're in car B instead, and if we look at car A, we will see for this particular moment in time that car A is stationary, which I think is quite an incredible result, really. And it tells us that if you're in a rotating system of coordinates, it is not the same as just subtracting the two velocity vectors to find the relative velocity. Instead, the safest way to do this is just apply Euler's equations and take into account this term, with this term here, which considers the rotation of the system of coordinates. And that's the end of the question.